Hi, in this video, we will see what is quantum Fourier transform and how to implement it in Classiq platform. So let's start with classical version of Fourier transform first, then we will see what is quantum Fourier transform. So in classical Fourier transform, consider this as a non-periodic signal or a sound wave for some duration from here to here, and x-axis is representing the time and y-axis is representing the amplitude in at a particular instant of time. Now this wave is made up of multiple sinusoids, like a structure or a house is made up of multiple Lego blocks. When we use Lego blocks to make some structure, then we use small blocks to make a structure. Similarly, this wave can be thought of as a made up of multiple sinusoid components. It might have too many sinusoids, but for the sake of simplicity, let's assume that it's made up of these three sinusoids. So Fourier transform, the function of Fourier transform here is to break the original signal into its sinusoidal components and represent it into the frequency domain. So Fourier transform takes the data from time domain, means it was represented as signal in the time domain. Then Fourier transform takes it and then breaks it into the individual sinusoid components and represents in the frequency domain. So here we can see that this one have very low amplitude but very high frequency. So in frequency domain, this will come here because this one have comparatively high frequency. Here this one have very high amplitude, so it goes here. This one have moderately at mid amount of amplitude and frequency, that's why it's here. So we are representing like this in frequency domain. Now Fourier transform have many applications, but one application we can think is that MP3 compression. So whenever we record certain audio, then there are many frequencies there which are not audible to human beings. Consider this frequency. It's suppose it's very high frequency and not audible to normal human beings. So what we can do using Fourier transform is that we can figure out the constituents of the original signal, and then we can just we can use some digital electronics circuit to filter out this frequency, and then we can use inverse Fourier transform to reconstruct the signal. Now the new signal which we constructed will not be the exact replica of this signal. It might be slightly different, but we will still hear the same sound which we recorded, because anyways the extra frequency which we removed, that was not audible to us. So what is benefit here is that we got rid of the extra frequency which was not audible, and that's why we compressed the data, means that's how we reduce the size of our data which we were storing, by eliminating the frequencies which were not audible. And here Fourier transform acted as a tool to take data from one domain to the another domain where it is easy to process the data according to our need. So let's see what our observations we have. So first observation we have is that classical Fourier transform is used as a tool to take data from one domain to another domain. In other words, to take from time domain to frequency domain. And yeah, it is used as a subroutine or sub-process to convert data. Same thing, basically. Now, while we are seeing this, let's go to quantum Fourier transform now, then we will understand. So quantum Fourier transform is also used as a subroutine or sub-process in many quantum computing algorithms. And what it does is to take information from computational basis to Hadamard basis and encode information in phase. For now, let's focus on first part of definition, means taking from computational to Hadamard basis. Then we will come to the second part, which means how to encode the information in phase. First, let's understand what is computational basis and Hadamard basis. So whenever data is in binary format in zeros and ones, then it is called computational basis. and when data is in this plane of equal superposition, then it is known as Fourier basis or Hadamard basis. You can also think in the way like if this is H, then if data is in 0 or 1, means if this arrow is pointing to either north pole or south pole, then it is in computational basis. And when it is taken in Fourier basis, it starts pointing somewhere in the equator, and it keeps rotating in this way. And here we are applying QFT to the 0 state. When we apply QFT to 0 state, it takes information to the plus state, and yeah, it is equivalent to applying Hadamard gate to 0 state, which we will see while implementing the circuit also. And when we apply QFT to the 1 state, it takes to the minus state. So now looking at this, you might also think that QFT is as simple as applying the Hadamard gate. So if there is multi qubit input, then also we can just apply the Hadamard gate and take the information in this Fourier basis. So yeah, you are partially correct, but let's see what is the wrong with that approach. So here we have multi-qubit state 101 in binary, which is equivalent to 5 in decimal. So here we are representing 101 like this. Now if we apply only Hadamard gates to these three, then it will go to plus, it will go to minus, plus, minus. But this is entirely wrong approach. Why? Because in definition only we saw that it takes information from computational to Hadamard basis, but it encodes information in phase also. That thing we are not doing here. In case of single bit input, we apply only Hadamard gate worked because there was single bit information and there was nothing to encode in phase. But in case of multi-bit input, we take to Hadamard basis, plus we encode information in the phase also. Let's see how we do that. So consider multi-qubit state 101. Then to calculate the rotations, we use this formula. Rotation of qubit equals decimal equivalent value upon 2 to power n, and n is the number of qubit, multiplied by 2 pi radians. So for us, its decimal value is 5 and number of qubits is 3, means 2 power 3 is equals 8, multiplied by 2 pi, and this 2 will cancel this 8 and here it will become 4. So we have rotations as 5 by 4 radians. Now how rotation works is that for first qubit we will do 5 pi by 4 radian rotation, means it will go from here to there. And then for second qubit we will do 5 pi by 4 into 2, which is equals to pi by 2. So it will go from here to here by 90 degrees, and then we will do pi by 2 into pi by 2 into 2. Again we will multiply by 2, so it will become pi, means it will go there. Suppose if there was one more qubit, then what we will do? We will do 2 into pi. So 2 pi will come 0 and we will come here at 0 degree. But right now we have only 3 qubits, so that's why we are stopping here. And now we can see that whatever we saw the definition of QFT, it took the information from computational basis to this Fourier basis, but also it encoded the actual data which was in computational basis. It encoded that actual data in as the phase in Fourier basis. So this is what we saw in definition. QFT takes state from computational basis to Fourier basis such that information of computational basis is encoded as the phase in Fourier basis. So yeah, it's same thing. Now let's see one more example. And before seeing one more example, here this diagram is not much clear, so I will just show this one. Here we can see what I wanted to draw actually. So for 101, first rotation is 5 by 8, means from 0 to this 5 by 8, and then second one is pi by 2, means from here to here, and then third one is pi, means from here to pi by 2 and then pi. So this is what I wanted to draw here, but it's not much clear here. So now let's move on to the another example, which is 8. and 8 we are representing by 4 qubits, and in 4 qubit it is equal to 1000. So this is computational basis 1000, and to calculate the rotations we will use same formula which we used there. Decimal value is 8 and number of qubit is 4, so it will become 8 by 16 into 2 pi, which is equals to pi radians. So let's do the QFT. First one is this one. So for first qubit we will rotate it by pi radians, means from here somewhere to here we will take. And second one we will rotate by 2 pi, and 2 pi means 360 degrees, so it will come back to the here. After 2 pi we will multiply by 2, which will come 4 pi. For 4 pi also it will come here, and then again 4 pi into 2 is 8 pi, again it will come here. So this is how we will represent 8 in the Fourier basis after doing the quantum Fourier transform. And again here also we can see the information is taken to the Fourier basis and encoded in form of the phases. And if we go to this link is provided in the notebook of Quantum Fourier Transform. Here we can see QFT of all states, from all binary states from 1 to 15, 0 to 15, and we can see here that initially data is in just 0 and 1, means either it's up or down. After doing quantum Fourier transform, we are taking to this Fourier plane, and there we are just encoding information in form of phases. Okay, now let's see one more example for 12, and 12 is represented as 1100 in binary, means 8 plus 4 equals 12, and here this is computational state representation, means 1100, and to calculate the rotations we multiply 12 by 2 pi and divide by 2 power 4, means 4 qubits here, which is 16, and it becomes equals to 3 pi by 2. Now let's see how we do the rotations. So for first qubit rotation is 3 pi by 2. For second it's 3 pi by 2 into 2, which is equals to 3 pi, and 3 pi is equals to pi, so it goes there. And again then pi into 2 equals 2 pi, means here rotation will be 0. And for 2 pi into 2 it's again 0, because 4 pi is also nothing but just 0 degree rotation. Now let's try to imagine how the circuit of quantum Fourier transform will look like. So whatever we saw till now, we saw that quantum Fourier transform shifts state from computational, means from poles to the equator, and we also saw that the rotation is done just around this axis is z axis, and rotation is done just around the g axis. So from this we can we are not going to draw a circuit now. First we will see the mathematical part, but just by looking this we can imagine that when we will construct the circuit we will use Hadamard gate to take here, and then we will use some kind of G rotation, means we will use G gates to carry out these rotations. We will see in more detail when we will implement using Classiq, but for now let's see maths for QFT. So QFT for state J is represented as G tilde, and it is equals to 1 upon root n summation of k equals 0 to n minus 1 e power 2 pi I upon n j multiplied by k, and then state of k. Here important thing is that this n is equals to 2 power n. So suppose if j is 3 qubit input, then this n is equal to 2 power 3 equals to 8. But for now let's see the 1 bit input, how QFT will work for 1 bit input. So for 1 bit input n will become 2, because 2 power 1 is 2, and the summation will go from 0 to 1. Here n is 2, means 2 minus 1 is 1, and expanding this summation we have this j tilde equals 1 upon root 2, and here in e power whatever we have power here that is multiplied by 0, and plus whatever is power of e that is multiplied by 1 here. since this term will become e power 0, it will become 1. So here we are eliminating it, and this term 1 is here, so it will remain, but this 2 will cancel 2, so it will become I pi j. Now let's use this formula to see the QFT of 0 state. So when we apply QFT to 0 state and put in the formula, uh, this 0 will remain as it is, and here when we put value of j as 0, this term will also become equal to 1. So it will become 1 upon root 2 0 plus 1, which is nothing, it is the value of plus state. Now let's see for 1 state. So this time for j value is 1, and e power pi I is minus 1. So that minus 1 is multiplied to this 1 state, and it becomes 1 upon root 2 0 minus 1. And this is nothing, it's just minus state. So mathematically also we saw that QFT of 0 is plus 1 and QFT of 1 state is minus 1. This thing we saw at the start of QFT only. We saw that QFT of 0 is plus state and QFT of 1 is minus state. Now let's see for multi-qubit input, means for 3-bit input we will see. So for 3-bit input we have this n will become 8 because 2 power 3 is 8, and summation will go from 0 to 7, which is 8 minus 1 is 7 here, and e power 2 pi I for 5 we are seeing. So here there is minor mistake, here it's 2 pi I xy, but it should be 2 pi I jy, and in place of j we are putting 5 and then y and then y state. Now if we expand this summation, then we have 5 tilde equals 1 upon root 8, and then this whole expanded thing. And important thing is that we are seeing 1 2 3 4 5 here. These are equivalent to 0 0 0 0 0 1, means all these are binary equivalent, but to make the expression short we are writing as decimal. And here we see that all these states are in equal superposition. So at this point, after doing QFT of state 101 or after doing QFT of state 5, if we measure it, then we will just see these all results in the output, because all are in equal superposition, and it might not be useful for us also, because we are directly doing QFT and measuring the results. So if you do QFT and its result are not giving any insights, just don't worry, because we will use it as a subroutine or sub process to do other things in next videos in like source algorithm or quantum phase estimation. But for now, let's move on. Also here we can see that difference between the phase of this and this is pi by 4, this and this is pi by 4, this and this is pi by 4, and so on. So this is another important insight. Now this is looking good. We see that here we have superposition of all state, but this expression is not giving us insight what rotation should be carried out for each qubit. So for that we will use this formula, and this formula is derived from this formula only. To see how it is done, you can refer the Quantum Fourier Transform notebook. Here it's described in detail, so you can see this. I will just go here and use this formula directly from bottom, this one. So here we have this thing, and I will just put the values in this formula, and by putting values I got this thing, 5 tilde equals, I think here it should be tilde, but tilde is missing, but let's imagine tilde is here. So it's 1 upon root 8, and then we have these 3 qubits. These 3 states mean tensor product of these 3 states, and by putting values and just simplifying them, we see that here we have 5 pi by 2 and 5 pi by 4. Now if we remember the rotations which we carried out in first qubit, it was 5 pi by 4. In second qubit it was 5 pi by 2, which is equals to pi by 2, and in third qubit it was pi. So yeah, this expression mathematically also tells us that whatever rotations we carried out for the 5 state were indeed correct. Also, one important thing is that if we multiply all these things and expand this tensor product, we will finally reach at this equation, this one. So these two are same thing, just a different way of writing same thing. And here we getting the insight also what rotation needs to be carried out. So now let's move on to the implementation part of implementation of Qiskit using Classiq SDK. So let's start with one qubit. And see how circuit looks like. So for one bit, we can see that QFT circuit is nothing. It's just Hadamard gate. So here we have 0 state and Hadamard gate is applied to it. Even if it was 1 state, then also Hadamard gate only will be applied. Now let's see how QFT circuit looks like for 2 qubits, 3 qubits and 5 qubits. So for 2 qubits, if I expand this QFT block, we can see the first qubit Hadamard gate is applied, and for second means it's in reverse. So for this one, we are applying pi by 2 rotation, and then we are again applying Hadamard gate. For 3 qubit, if we see the circuit, here we are applying Hadamard, then pi by 2 rotation, then Hadamard. Then for upper qubit, we are applying pi by 4, then pi by 2, then Hadamard. Again, if I expand it for 5 qubit, we will see that it starts similar to 2 and 3 qubits. First we apply Hadamard, pi by 2, then Hadamard, and for next qubit we will go pi by 4, pi by 2, then Hadamard. Then for upper one, we will divide by 2, means if it's pi by 4, here we will start from pi by 8. So pi by 8, pi by 4, pi by 2. Now if you guess what will be for this one. So for this one, it will be pi by 16, pi by 8, pi by 4, pi by 2, then Hadamard gate. Now suppose if there was one more qubit at top, then it will start from pi by 32 instead of pi by 16, and it will keep increasing. And these gates which we are seeing are nothing. These are just controlled G gate rotations or Z gate rotations. So in during discussing intuition only, we discussed that we use Hadamard gate to take to the Fourier basis, and we use then G gates to do the rotations, and we are using control G gates to do rotations. Here I will just show all them together. So here we can see whatever we discussed. For 1 qubit Hadamard, for 2 qubit Hadamard gate, then control G gate which rotates by pi by 2, then Hadamard gate. And there, suppose if there is one more qubit, then it will start from pi by 4 instead of pi by 2. And if there is one more qubit, then it will start from pi by 8, for more pi by 16, and then we will just keep incrementing the bottom value of 2. Means we will pi by 64, pi by 128, and so on. So that's how we implement. And here let's do the QFT of 5, which is here we are preparing the state. Here we are passing the probabilities. These things we discussed in state preparation notebook. So here 0, 1, 2, 3, 4, 5. For 5 I am giving probability as 1. So this state will prepare to the 5, and then I am doing the QFT of it. So let's see. Let's run this and see how output and circuit looks like. So here first we are doing a state preparation, means it's 1, 0, 1. These are not gates, and then we are doing QFT. So same pattern again, you can see H gate, then pi by 2 rotation, then H gate, then pi by 4, pi by 2 rotation, then H gate, and at the end we use swap gates. And now if I execute it, as we discussed in mathematics part, the outcome which we will see will not be much helpful, because for all values from 0 to 7, we are just seeing that all have equal chances of getting in the measurement, which we saw in this formula also. Means all have equal chance to get measured here. Now let's see, like we saw that there is quantum Fourier transform, and there is inverse Fourier transform to undo the Fourier transform. Similarly, we have something called inverse quantum Fourier transform. So it is used to take the information from Fourier basis back to the computational basis, and it is used in source algorithm and phase kickback, which we will see. And it is represented by a QFT dagger. And if we see the formula, this is same like QFT. Only difference which we see here is this minus sign in the exponential, this minus sign. Apart from that, formula is same. Now let's see inverse QFT. So what we will do, first we will do the quantum Fourier transform of 5, and then we will do inverse quantum Fourier transform using this part. So for inverse quantum Fourier transform, we just need to pass is inverse as true, and then we will see that we will start with 5 state, and we will do quantum Fourier transform, and by doing IQFT we will again come back to the 5 state. So let's synthesize the circuit and run it. So here we are doing state preparation first, 101. Then we are applying quantum Fourier transform, which we saw. Then after that we are doing inverse quantum Fourier transform. So here we apply these Hadamard and rotations. Then we do swap gate, and then here we are first doing swap gate, and then we are doing these rotations. And also if you notice, these are control G gates, but these rotation signs are in minus, and then we will measure. So after executing the circuit, we can expect that whatever we feed it, that we will receive as output. So yeah, indeed we got 5 as output. So this was video on quantum Fourier transform. Thanks for watching.